Hello Internet, we are back with our Arduino project. Specifically, we're going to get a little bit more into what we're actually building. I have the parts now, so we can actually start building that. So we've got the thing we built last time running still, but the Arduino looks a bit different, if I can just get that up there. So there's a new chip, actually there's two new chips, and we've got a battery on top of there. So we have a lithium-ion battery that can power the entire thing. It's not being run right now because it's connected to my computer, but that's there so we can actually have power, and it does run if I don't have it connected to my computer, which is fantastic, so we can actually power this thing on the go. And then we also have this other the smaller chip there connected to the breadboard was a accelerometer and a magnetometer. And so that measures two things. The accelerometer is going to measure your acceleration, specifically acceleration based on gravity. So you get a down vector. And then you also have a magnetometer, which is going to track magnetism. So that's going to get pulled north. And so with that, we can get two directions for where we are. And I'm hoping we probably don't actually need the other one. But the entire idea of this is we are going to build a compass into a belt. So this is approximately the size of a belt that you would need. Anyway, and it's got enough LEDs so we can actually hopefully take the direction, the Y direction effectively, the up and down, spin that, figure out where that is, and actually calculate a point that is the closest to the north. It's going to be a little bit weird because obviously it's a belt, so you can actually resize it. But we're going to ignore that issue and just kind of get it close. And so that's sort of the idea, is generally create something that shows you north. And then we can add more to it. So we have all the parts that should make this possible. So that's what I'm going to be getting into now. So I have these two projects open. The one running currently is over on the right. It's kind of covered up by my camera right now because we don't really care about it. We've already looked at that. The one on the left is new. I haven't really changed this besides gridding in orientation. Oh, that's not going to work. And so the orientation is going to be in degrees for how the magnetometer is oriented. So if I upload this, our lights are going to stop eventually once this actually compiles and uploads. One of the side effects of that is the LEDs, you can see they stopped. That's because it sets a state like we had to clear it before. The state is set, so as long as we have power running to this, and we do because it's still connected to everything, the previous state is still going to be shown. But we now have the new sketch running, which we need a serial monitor to see. And that's actually going to display, if I hold this up, you can kind of see it change a little bit. But as I change this, we get new readings. And so that is in degrees, that's the coming off the magnetometer. So what I want to do is take this and translate it into a normalized vector. So that's just going to be some basic trig. Get that into a vector. And then once we have that point, what I want to be able to do is take that and then take the dot product with the expected north. For that, we're going to have to know the orientation, the expected orientation of that, and we're gonna play with that because this is as far as I've gotten with playing with this chip. So we're gonna see how it goes. That's weird. Why was it 0? Anyway, now that we get that, we should be able to actually use that. Once we get the two dot products, we'll be able to actually calculate that. The problem is we don't have any way of calculating dot products. So we're going to need to implement some way to do 3D vectors, to store those 3D vectors. And we're going to need a way to calculate the dot product of two vectors. So that's what we're going to be working on today. So let's see here. You can see all of my cheating stuff. I was reading up a little bit more about how dot products are working on, just refreshing my memory. The way the definition, I guess, of a dot product is, it is the two lengths of a vector, of two vectors. So vector A and vector B, if you multiply those two together and then multiply them by the cosine between the two, that's the dot product. which is really that's going to be hard to solve. So that's less useful. The more useful definition is if you take each component of a vector, say the x, y, and z components. If you take vector A and vector B's x coordinate and multiply those together and then add those to the multiplication of both y's and both z's, that also gets you the dot product. And then with that, you can actually derive the angle because it's just the length and then the cosine. So that was a very, very long definition, but we're getting there. So what I want to do is we switch these two. So now I have our accelerometer or a magnetometer set up over here and our neopixel stuff over here. I need to define a struct. So Arduinos work on C. I believe it's C. Hope it's C. C, C++. I actually don't know which. But we need to do some type defs. So this is how you sort of create a class or a struct. There's no real class idea. It's structs. And they look a little bit funky. So this is going to be our vector 3. And then you have to end that with a semicolon. And so this is, we're defining a structure, a set of memory, a block of memory that is going to define a certain type, which is going to be a vector 3. And then the semicolon just ends that. This is going to be the same in C++ or C. It's the same style. And then let's store it with doubles. And we're just going to want double X, double Y, and double Z. Now, I should point out, I am not a C++ expert or a C expert or anything in between. I haven't touched it in a while. So this could go poorly, but we are going to see how this works. So now that I have this X, Y, and Z, I'm actually going to... First, let's get all of this code over here. So there's a lot of stuff that happens in this little thing. We can just pull most of it over. So we have the includes. Then there are two global definitions. There's the accelerometer and the magnetometer. We are only going to be using the magnetometer for now. I don't think we need the other one yet. But if it turns out we do, then we can grab it. But we can set up both of those there. They get an ID just so they're identified. And then display sensor details. Sensor get sensor. We don't need to display any sensor details. I don't think we need that. Let's see here. Then we go into our setup. What's this doing? If not serial. I don't know what that's supposed to do, but okay. Looks like an infinite loop. Yeah, so this is going to pause it until a serial terminal is open. That's okay. We don't need to worry about that. We're not using a Arduino Zero or Leonardo board or anything like that, so that doesn't matter to us. This is setting our serial output so we can actually print things to the screen. We did that earlier with DataCube. We don't need to worry about that here. We're not going to, well, let's set that up so we can actually start printing things. That seems like a smart idea. Now this code is going to be super rough because we're still figuring things out. We're still getting everything set up. And so because of that, it's not going to be the prettiest code, but that's kind of by design. I don't want to start abstracting this out and start pulling things into methods before I know what it's going to do and how it's going to look. When I don't know that stuff, it makes it really hard to do that. If I try to do it now, we could do it. It just wouldn't be a good abstraction, so we might as well just avoid it for now. So the next thing it does is it defines an event. So we will stick that here. And we just have our sensors event T. That's a type imported from this library, actually, the Adafruit sensor library. And so that comes in, And then I was actually grabbing both the accelerometer and the magnetometer thing. You can see I currently have the accelerometer display disabled, but it is there. And so let's grab that. And all the way down here, we just want to, inside of this, print out our value. This is not a great place to put it because it's after all the lights have gone. Well, let's actually move that up. That might make a little bit more sense. This might cause the LEDs to run a little bit slow because we're doing a bunch of like serial commands and stuff. We'll see. Hopefully not. But what this should get us to do is we should now get that serial output and we should get the lights moving. And if not, then I've screwed something up. So I'm going to compile and start uploading that. Looks like it uploaded. We should see the lights start going. And I'll open up our Arduino. Yeah, so the lights have slowed down considerably. They're not as fast, and that's just because this code is not, it's not timed. It's not based on any specific timing. It's all based on the speed of the program that's running it. And so when we slow it down by adding all this I/O, that's going to just make it slower. And so that's what we're dealing with. So we could probably speed it up actually by taking those out. I suspect the I/O is slow and not the reading of the event. That's just pulling things off of memory. I could be wrong. We'll see. This will be more visual. If the lights are going faster now, we'll see it. We won't see anything printed here anymore though. So yeah. So it's quite a bit faster now that we're not doing I/O, which is good. It means when we pull out the I/O operations later, it means everything's going to speed up and our thing is going to get more responsive. And so the speed that we're doing this is going to represent how fast we actually respond to that magnetometer. So that was a long ramble, but we're going to re-enable this. And then what I want to do is actually create a new vector. So we're going to have a vector 3 of our direction. We'll call it the orientation. So currently the orientation is measured in degrees, and it's the degrees of this magnetometer. So it should be that way. That's north. Kind of irrelevant when you're on a camera. Different for you guys, but for me, that's north. And so that's sort of the way we want this to face, but we want to actually build that vector. And this is the part that I don't really know how to do. So we're going to do an orientation equals a vector 3. That's not going to work, is it? Because if I just do 0, 0, 0, I don't think that works. But I could be wrong. And I'm actually going to plop this here. And then we're going, instead of printing out those degrees now, we're going to print out the orientation. And so this should just pull off the vector from this, or from our new calculation. And so we'll just say I want this to be 1, 2, 3. I don't expect this is going to work. I expect we're going to get a syntax error, but we can work with that. Yeah, candidate expects one argument. Copy constructor. It's expecting a copy constructor. So, actually, I should just be able to do this. This isn't the most efficient way, but saves me having to do other stuff. So that when we define this block up here, the block I've highlighted, the vector 3 there, that is a chunk of memory. We're allocating a chunk of memory and saying I want to store something here. And then the reason this works, why I don't need to create a new one, is because by allocating that memory, I already have. So the structure already exists. Once I declare that variable there, the memory allocation, or the memory exists. I can store stuff there. And so that's sort of what I'm doing. It's not the most not the most efficient, I guess, but it works. And so this way we get X, Y, and Z. They start printing out. We're good there. Now we need this to actually be useful, which means this X, Y, and Z need to actually come from something. So we actually want this to be the event orientation.x, event orientation.y, and the event orientation.z. Now these, if I write those out, should start printing off exactly what we were seeing before. We should just be getting those same values again. And we are. So that's all working. But what I want to do is actually do something a little bit more with that. We need to figure out how to define our object. And so assign is going to give it be 0 degrees is going to be 0, obviously. And then 90 degrees would be 1. And then 180 would be 0 again. And then 270 would be -1. We need to define all of this. I don't know the best way to do that. Let's start with cosines. I think this is wrong, but we'll know pretty quickly. Yeah, we'll know if this is wrong. The reason we'll know is I would expect this to be 1. I would expect it to be normalized. I'm making this up. So if that's not what happens, oops. And I'll figure that out afterwards. But I'm pretty sure if I get this right, we should get a normalized vector out of it, because the sum of these 3 angles should equal a normalized vector. I'm like 90% sure that's correct, but I never validated it, so oh well. Also, I don't think math is included. Oh, it is. Well, that's much easier. So there's a math library where these would come from, math.h. That doesn't look right to me. If I stop the auto scroll, you can see the numbers are bigger than 1. Actually, pretty close to 2. Not exactly 2. Why not exactly 2? Okay, I'm going to go look up how to convert Euler angles into a vector, because I need to figure that out. I'll update you once I figure that out. So 1 sec. Okay, so I have this fun little equation. This reminds me a little bit more of what I actually learned how to do this. And so this gives us the actual results. They're using yaw, pitch, and no roll. So yaw and pitch. Yaw is going to be our x on this orientation. So anytime we see yaw, is that? No, pitch. Pitch is our x. And yaw is going to be our y. So yaw is going to be side to side. Pitch is up and down. So that's going to be x and y. So yeah, we should be able to work with this. Pitch, sine of the pitch is going to be x. There's actually a rotation matrix that you can actually create out of this and then multiply the direction by that. That would do the same thing. We're just not using that right now because that's just more work. So cosine of our event orientation dot. I'm actually pretty sure this has pitch as an option. I have the docs pulled up quick. Yeah. So I could actually use pitch if I wanted to. We're just going to stick to x. And then event orientation dot x. This is going to be cosine of our yaw. So cosine of yaw is y, not u. And then we have our cosine of our event orientation.x, which is our pitch. So this should give us our directional vector, I hope. If not, then that I'll need to do some more research. I believe this reminds me of what I was sort of expecting. Still bigger than 1. That would, well, would it have a length longer than 1? Yeah, it should. One moment. I'm gonna need to go do some research and actually figure out how this is working, because I think I'm screwing something. Well, I know I'm screwing something up. So let me go figure that out, and then we'll pick this back up. Okay, so turns out these sine functions, these cosine functions, accept sine, or they accept radians, not degrees, which is why we're getting these numbers that I wasn't really expecting. That's because we're using the wrong size. Luckily, the library that comes with the sensor, the magnetometer and accelerometer, has a sensors DPS to rads, which is just a constant value, which takes degrees to radians. And so that should get us down to what we want. And if not, we'll start having to divide or define our own version, because this should be what I'm expecting. This should be the constant that I'm thinking, and then we'll get to where we hopefully we'll get the values that we're expecting. So we'll get unit vectors. Still not unit vectors. That seems too auto scroll. I think what we're running into is floating point errors, but I'm not sure. That doesn't look right to me. 9.6.25. These values they're not what I was expecting. I would have expected to get a unit vector out of this, and I'm not. At least I don't think I am. This shouldn't be a unit vector. And I saw we had 1 before, though this was at least close. I'm curious where this imprecision is coming from. And I don't know I don't know where it's coming from, whether the cosine and the sine functions are just imprecise, and so it's sort of an approximation, or if something else is going on. I really don't know. It seems close-ish. But it's hard to tell. Yeah, it's really not easy to tell what's going on. Sorry, you can't see that, but I'm rotating it trying to figure out what is going on. Huh. I think I'm kind of tempted to call this good enough, which it almost is, but we'll see. So for the example of this test, this is almost in north. This is almost northern orientation. We're gonna ignore these imprecisions. I'll fix those on my own if they actually are a problem. But for now, we're just gonna move forward because that's just what we need to do. So this is at least close enough to north. So z equal to 1 is north. So I'm actually going to, right up here, define a vector 3 of true north. Is this a good idea? This might not be a good idea. And we'll say this is equal to 0, 0, 1. Does that work? That might not work, but Again, figuring this all out again. It's been a while. Nope, really didn't like that. All right, fine. Hold on, I should go figure out how to actually do this. I'm gonna write this out so we have a perspective on the wrong way to do it, the way I've been doing it, and then I'll figure out how to actually do that better. So one sec. No, there's a lot of breaks, but yeah, it's worth it. Right, so the way to initialize these is just by doing this. And so this initializes the first three variables, fields in the struct. So this will be x equals 0, y equals 0, z equals 1. And semicolon, because those are important. And then if I verify this, this should work. Yeah, awesome. So then we can actually switch this down here as well. Do we want to? Yeah, we'll leave that one for now because that's its own little thing. But for now we have TrueNorth and we have our orientation. So what I want to do is calculate. Let's move this up. And we're going to do a double. Everything else is in doubles, so we're going to work with doubles here. And this is going to be our dot of vector 3. And we'll just do 1 and vector 3, 2. So not the most clear naming, but I can't think of anything better to name two vectors. So vector 1 and vector 2. That'll have to do. All right. So the way this works is we are going to return 1.x times 2.x plus 1.y times 2.y plus 1.z times 2.z. That's your dot product, right? Super simple. There's nothing complicated here. And so the way this works, say these are in two opposite directions. So say you have two vectors, one's -1, 0, 0, and one is 1, 0, 0. If we walk through this, the way this works is we would expect the dot product to be -1 because two opposite normalized vectors will have a dot product of -1. And so in this case, 1.x, -1, and 2.x, 1. So that is 1, or -1, sorry. And then both of these are just zeros. So we get -1 plus 0 plus 0, just -1. And so that actually works for pretty much anything. So that's that, hopefully. So now we can actually use that. And I want to print out this dot product. So we're going to have a double dot orientation. And so that's going to be equal to the orientation and our, sorry, that's not right. We're going to take the dot of our orientation and TrueNorth. Both of these should be almost normalized because they aren't exactly. We may run into some issues, but this should get us a normalized vector. Then serial.println, we are going to print out the dot orientation. And so that will just print out that orientation for us, and we'll actually be able to see if we're close. So if I orient this north, we would expect it to be 1. And then as I get further and further away, we would expect that to get further and further off. So let's upload that. I'm actually, I'm wondering if I actually needed to do this. We'll see. So that's 99. I want to follow this. We're at 1, so we're in line. As it gets off, I would expect this to be negative. So this is pointed in the opposite direction. That's that's less good. This is not going as expected. Mostly because I'm messing with a ton of wires, and I don't think it's going straight down. I think that's where part of the problems are coming from. Like you can see, I almost had one there, but either way, doesn't really matter. How are we going to get, now that I've done all of this, how are we going to actually get, because the idea is from that, we're supposed to be able to look up a pixel in here. So effectively this would be like our 0 and then it would work around or something like that. How are we going to do that with just a dot product? How is that going to work? Oh, I don't know. I think the better way, by better I mean maybe potentially better. Now that we've done all of that, I thought dot products were going to be a good solution because it'll tell us if we're in line with that. Maybe not. not potentially, or not necessarily. I have another idea that we could use them for, and that would be like maybe you orient it sideways and you're not necessarily in line with the plane. In that case, we could kind of spread it out and kind of give you less perfect results. But I already have the yaw, or the yaw. I already have the yaw of this. So let's grab that and just work with one of these. So if I do serial.println and we print out the event orientation.x, we'll need to figure out which one we're going to want. But one of these is going to give us the rotation, the yaw in space. Based on this orientation, it's going to obviously change as we do that, but as I rotate it here, we get, is this correct? It should span between 180 and not. So if it's not, we're doing something wrong. I think that's the wrong thing. Oh, there we go. Cool. So let's try y. .y. There we go. See what this gives us. Again, kind of playing with this. It does have markers for the actual axes on this, but I haven't found those to be very accurate. And maybe this is just because I'm in a building way up in the sky, but see, neither of these give us a full range of motion because these are degrees, remember, so we would expect either between something with a range of 360 degrees. If we're not getting that, something's going on, because that's what we need. So I would expect it to be like, I'm getting a wide range, but it's at like a 45-degree angle, which might be a problem because I don't walk at a 45-degree angle. And if they're all sideways like that, that's going to be a problem. Anyway, I'm going to figure that out at a later time. We've spent way too much time trying to figure that out. So, given this event orientation.y, what I want to do is for int I don't know if you should be able to do this. For int, we already have I defined, so I'm going to do int n equals 0, where n is less than the, what do we call the number of pixels on this strip? The number of pixels plus n. So for every pixel, I want 2 pixels dot, I think there's actually a clear. So let's do that instead. Let's clear the pixels. And then we need to look up based on the orientation where we are. So this can go between negative 180 and 180. I'm going to get that into normal space. So 0 to 360. And so to do that, we're just going to add 180 to it. And then we're going to divide it by 360. So double current index. Yeah, we'll say that. Current index is equal to the event orientation.y plus 180. So this gets us into positive space. And then if I divide this by 360.0, the 0.0 is to make it sure we're doing floating point division. Otherwise, at least with Java and stuff, you run into issues where it doesn't cast it. And then you end up with just float or ints, which wouldn't be good if we're going all the way down to 0 to 1. Everything would just be 0. So this will get us between 0 and up to just less than 1. It won't give us 1 because we shouldn't get 360 ever. And since we don't ever get hit 360, we won't ever hit 1. But it's enough where we can actually index onto these LEDs. So all the pixels are cleared. We have this. I want to comment those out. We'll keep the delay there. And then I just need to take this set pixel color right here. And instead of we are going to use the current index times the number of pixels. And I can either, I think round is defined, so we're going to try to use that. This should go, well, let's take the floor. And that will prevent us from getting out of bounds when we get to high values. And so floor is going to say, we're effectively multiplying this number by the number of pixels. So we're getting an index base out of this by this times the number of pixels. So effectively we are translating a rotation into a point in our array. And so now that we have that, we can use the floor. And so since there's more precision in our orientation, in our direction, we can create those different gaps. And so this should fall into that. So hopefully by doing this, we'll get 1 pixel somewhere to light up. I don't know exactly where that's going to be because we've been having those issues with the orientation. But hopefully, yeah, so you can see it's kind of behind me a little bit. But as I rotate this, it kind of follows it. And so once I can actually figure out how to get the orientation correct into my space so it's looking straight down, and that may just be using the accelerometer and stuff, but once I can get that, we'll actually be able to trace and actually use these lights. Let's see if I can do something like that. Kind of comes back because we're fudging the math, but you get the idea. We have a point that we can move around based off of this sensor's reading. And so based on where we put that sensor, we should be able to get a point on this that actually makes sense. So hopefully we've just tied orientation into our belt thing. That's sort of where this is planning to go on. I have some belts back there. We'll get into that in a later video. But that's sort of the general idea, is to take orientation and transform it into something we can, oops, drop on the floor, but use. So that's that. So this one ran a little bit long because my math was wrong, and I did a whole tangent on dot products and then realized, oh, that's not actually going to do what I want it to do. But hopefully that was interesting and you guys learned something new. If you have any ideas or fun project ideas that you want us to cover, let me know in the comments. That's the best place for me to get ideas. So love to hear what you guys are thinking. If you guys want to have fun projects and want to talk about them or share them with other people, we have a Discord channel where a bunch of people are sharing their projects or just talking about cool things in tech. So come and check that out. Otherwise, I will see you guys in the next video. So until then, see you, Internet.